Welcome to Structural Geology Lab 1, looking at topographic maps. Topographic maps are maps that show elevation. They show elevation using contours over a wide area. They can be showing elevation of the ground surface or some other surface such as groundwater, rock formation tops, glacier surfaces, or even other surfaces. A contour line is a line that has every point along it as the same elevation. It's kind of like a staircase. On a staircase, if you look at it from the front, the edge of a step is a line. You think of that as a contour line. That step is horizontal. Everywhere along that line is the same elevation. If the steps are at a 1 foot interval because each step is 1 foot high, then everywhere along the first step is 1 foot above the ground. Everywhere along the second step is 2 feet above the ground. Everywhere along the third step is 3 feet above the ground, and so forth. Every point between two contour lines is some value between those two elevations. So anywhere between the first and second steps is some height between 1 and 2 feet high. Very straightforward, but vital to understanding a contour map. Between the first and second step are values such as 1 1/4, 1 1/2, 1 3/4 feet above the ground. If you're 3 feet above the ground or 12 feet above the ground, it can't be between the first and second steps. That's impossible. That's a key feature of how contour lines are defined. Another important thing to understand about contour lines is the spacing. When contour lines are close together, this indicates a steeper slope. Again, think of a staircase. When the steps are spaced tightly together, you have a steep staircase. When the steps are very wide, spaced far apart, you have a shallow slope. It's a shallow staircase. If it's spaced far enough apart, it's virtually flat. When you have a very flat place like Grand Forks, North Dakota, or any place in the Great Plains, the contour lines are very far apart, unless you're using a very fine scale. If you're making a contour map on a 1 foot interval, you can see a lot of contour lines even in a place like Grand Forks. If you're making a contour map with like a 10-meter contour interval, you'll have almost no lines whatsoever in a place like Grand Forks. Move to some place like in the Rocky Mountains, and even a 10-meter contour interval is going to be incredibly dense with lines, possibly too dense to even make sense, and you may need to move to like a 50-meter interval just to really see what's going on, depending on the scale of your map. Another important defining feature of contour lines is that they don't merge or cross, with a few very special minor exceptions. If you have a truly vertical cliff or overhang, the contour lines can merge or cross. And this is because if you're looking truly straight down for a map view, then for that same location looking straight down, there is a place where the ground can be both high and low, because there is some ground that is high and some ground that is low at that same GPS coordinate, for an easy way to describe it. It's sort of like in a building, if you have an elevator shaft, it's moving straight up and down. You're in the same place, you're just at a different height. The other way that a contour line can meet up with another contour line and touch is if you have a valley between two hills and the low point of that valley happens to be precisely at a contour interval. And I'm talking precisely. If it's not precisely at the contour interval, if it's 6 inches above or 6 inches below, then your lines will come close but not touch. But if it's, the low point between the two hills is, for example, exactly 15 meters above sea level, and you're using a 5-meter interval, and so one of your contour lines is at 15 meters, then the 15-meter contour line around the eastern hill and the 15-meter contour line around the western hill will touch each other at the low point in the valley between the two hills, and so those two contour lines will touch. Many geologic structures are clearly visible on topographic maps once you get used to understanding what you're looking at. Understanding steeper lines and more widely spaced lines and shapes of the lines, and recognizing valleys and hills and mountains and slopes, and picking out things like rivers and terraces and plateaus and mountains, and identifying whether something is a river valley or a glacial valley, finding hanging valleys, finding basins, finding domes, finding anticlines and synclines, finding rifts. All these different kinds of structures can be clearly visible on topographic maps once you understand what you're looking for and once you learn and recognize the structures themselves. Geologic maps are slightly different. Geologic maps show the uppermost rock units over an area. It may be the exposed bedrock, or it may be what would be exposed if the soil and vegetation were removed. So it is the uppermost rock, whether it's exposed directly or whether it has soil and vegetation over it. And this is determined from outcrops, road cuts, direct exposure, and from wells. When it isn't exposed and there's limited data, they use interpolation for the areas between the data points. More on interpolation shortly. Geologic maps do often include topographic elevation lines, but not always. Sometimes the boundary of an exposed rock unit follows elevation contours. Sometimes the rock units cut across the lines of the topographic map. This tells us something about the structures. This tells us about the rock units. If those rock units are parallel to topographic lines, it tells us that that rock unit is horizontal. The edges are at the same elevation. So if all the edges are at the same elevation, because all the edges are mirroring, are parallel to a contour line, that unit is horizontal. It hasn't folded, it hasn't tilted. It's still in its original position. On the other hand, if it's crossing contour lines, it has tilted, it has folded. That tells us that there has been disturbance. It's not in its original position. This can help us with the sequence of events. This can help us recreate and understand what's going on. Cross sections show rock formations and structures from the surface down into the ground along a specific line. It's kind of like the side view of a layer cake that's been cut in half. We're looking at the inside down into the ground. It's like the road cut in a mountain that's been blasted to put a road through. Cross-section data can come from outcrops, from road cuts, and from boreholes such as water wells and oil wells. Sometimes they use seismic survey data and other geophysical survey data. And then the geologist takes all of that and creates a cross-section. Cross-sections may be small areas, a few 100 feet or 1,000 feet across, a couple 100 feet down, or they could be miles and miles across. Depends on the scope of the project and the data set available. Topographic maps, often called topomaps, can be hand-drawn based on personal interpretation of the data points, or the lines can be calculated by various means. Freehand mapping is drawing the map based on personal interpretation of the data. Interpolation is the name given to calculating the values between data points. And there are many different ways to do this each of which has special benefits in strengths and weaknesses and is used for different kinds of data in different kinds of situations depending on what you're looking for. Freehand mapping is the oldest method of drawing maps. It can be very accurate. Just because it's older doesn't mean it's bad. If the cartographer is looking at what they're mapping and is skilled, it can be incredibly accurate. It can also be incredibly inaccurate. If there's not a lot of data, if the cartographer's not looking at what they're mapping and is just using data, and if they're not very experienced, it may not even come close to resembling reality. And it can be anywhere in between. Most geology students learn this method early on. Even in Geology 101 type classes, you're given a little area with some data points, whether it's mapping groundwater or mapping ground surface. You're given 10 or 15 data points and asked to draw the contour lines. That's freehand mapping. Interpolation is a more standardized method of mapping. This is how computers make maps from data points. It's not automatically right. Just because computers do it doesn't mean it's always better. It is an estimate. It is a mathematical prediction, but it is standardized. Mathematicians and cartographers work very hard at improving it, and it's good, especially if you know your data type and what you're looking for and choose the right kind of interpolation. And if you apply it correctly. But you should never assume that just because the computer printed it out, that it's gospel truth. We're going to learn one method of interpolation that can be done manually, although even this method requires a computer for large data sets. We're going to work with a small data set so you get an understanding and appreciation for what interpolation is and how it differs from the freehand method. But the main thing is that freehand is personal, artistic interpretation, whereas interpolation is all calculation. The method we're going to learn is called linear interpolation. It's also called triangulated irregular network interpolation, or TIN for short. So linear interpolation is the same thing as triangulated irregular network interpolation. This is the simplest one to do by hand. That's why we're going to work on it. I'm going to use a very simple example with 4 data points here. Then I'm going to do some still shots. Then I'm going to have a video that has more data points and shows it full out. And then you'll do one with different data points. So the first step is adding your data, or in the example of the lab, your data points will be given to you already on the map. Then you connect your data points, creating triangles. Don't cross lines, so never cross lines, but never leave 2 points unconnected if you can connect them without crossing a line. So basically you're going to make as many triangles as you can without ever crossing a line. So don't skip connections and don't cross lines. Make all of the triangles you can. Think of it as like a little puzzle game. With the 4 points, I can make 2 triangles. Then we're going to start adding data points between our real data points. The ones we're adding are calculated data points. To make these, we have to figure out how many and where they're going to be. Between the 50 and the 100, to find out how many and what intervals, we have to know first what contour interval the map is at. In the lab, that's given to you. In this case, I'm going to do the map on a 10-meter contour interval. That was predetermined. I didn't label it, but this is a 10-meter contour interval map. I take the higher data point, subtract the lower data point. 100 minus 50 equals 50. Divide by the contour interval, and that lets me know that I need to have that many data points along the way. Finally, I actually put a ruler and measure the length of the line, divide by how many segments I needed, and figure out how long each segment needs to be. So if I measured and that line was 5 inches long and I need 5 segments, each segment needs to be 1 inch long. If it was 6 inches long, each segment would need to be 1.2 inches long. You have to measure it and divide and go from there. Each one will be different. You have to do this for every segment. You can see here that they all work out differently. Between the 100 and the 120, I only needed 2 segments. So it gets the 110 right in the center. Between the 10 and the 120, it got a lot of segments. Nice and evenly spaced. Now, already, hopefully, you see that this might not be reality. In reality, not every slope is evenly spaced. Between that point that was 10 meters above sea level and that point that was 120 meters above sea level, the slope might not be even. It might not be a steady, even slope. Not every slope is. But mathematically, that's a calculation, that's an estimate. That's the best we can do without any other data. With no known value between them, that's a mathematical estimate. We can do that all over the map. The more data points we have, the more accurate it'll end up. The fewer we have, the more we have to calculate. But once we have all of this, we treat our calculated points as if they were real data points. And now our map is covered with all of this data. A lot of it's calculated, some of it's original real data, but it's covered with data. So we have lots of places to draw our contour lines. That's what we need. So we can go in and we can connect all of the 20s and connect all of the 30s and connect all of the 40s and 50s and so forth and fill the map with contour lines. At this point, I've added all of the contour lines, but you can see the triangles still. Geologically, the contour lines are supposed to be there, but the triangles were just for helping me create the map. They're not part of the topographic map. So to finish up, what we do is we add Sharpie, something that won't erase and it helps us see the contour lines. We do that only on the contour lines, not on the triangles. Then we can erase the triangles, leaving a nice contour map. Now at this point, I could scan the contour map and submit it as part of my lab assignment. And we can see from this that I came up with a nice gentle hill slope. Looking at those 4 data points originally, it wasn't obvious, and this isn't the only possible explanation from those data points, but this is the interpolation of those data points. And it's important after you've interpolated the data to use your logic, to use your geological understanding and say, does this make sense? Well, there are hill slopes like this in real life, especially since this looks like it's probably a small area, so it's part of a hill slope. Perfectly realistic looking. So this is acceptable.
Now there was a problem with the recording. It cut off right at the end. So, because basically my phone ran out of memory. And so what I've done is I've taken a snapshot of the map as it was at the end of what I thought was being recorded, and I will talk you through the last little bit of it with that still image, but almost all of the interpolation is live recording. Okay, welcome to the topographic map hands-on portion, where we'll show you how to do the freehand style and how to do the interpolation method. Now it's important that you do the freehand map first. If you do the interpolation map first, it will not show you the difference between the two, because it's possible to make the freehand one come out just the same. It's just not very likely to match if you do the freehand one first, and that's what we want to see. So this is a different data set than what you have in your lab. So I'm not doing the lab for you, but need to cover the basic rules. What I'm going to do here is I'm going to do a 5-meter interval. So 5-meter intervals, and what we want is always on the even tens in this case. So 40, 45, 50, 55. We don't want to do something unusual like 43, 48, 53, 58. That would be technically still a 5-meter interval, but it's not standard practice. Standard practice is always on the multiples of 10, usually an interval that allows for that, a 1-meter interval, a 2-meter interval, a 5-meter interval. It's very rare to see like a 3-foot interval map. In a lot of places, it's anywhere from 10, 20, 50, or 100-foot intervals, depending on the topography. If you're in some place like the Rocky Mountains, you need to do a much bigger span of distance of elevation between each line. So like 100-meter intervals will allow you to draw the Rocky Mountains pretty reasonably. If you did 100-meter intervals for Grand Forks, you would have a blank white sheet of paper because there is not 100 meters of topography with difference in the whole city. I don't even think the tops of the buildings are breaking 100 meters relative to the ground. So, in this case, these elevations are all in meters. If the rest of the map was visible, there would be an elevation key and a north arrow and stuff like that and a location, but this is just an exercise. So the best way to start that I find is to either start with the highest or the lowest. I'm going to start with the lowest, and I'm going to see, okay, the lowest elevation I have on this map is a 27. That is below a 30-foot line. And I know if I look nearby, there's a 43 and a 50. The next things it's reaching are all above 30. So I'm going to put in a 30 line closer to the 27 than to the 43, because that just feels logical. It's a little bit arbitrary how I curve it. I curved it like that. It could completely reasonably curve the other way. There is not enough data density to tell us which of the two is correct. Either one is fine. You can make adjustments later. It's a good idea to be doing this in pencil at this point. I'm doing it with dry erase markers, even easier to change. So I'm going to label that 30. You can label it at both ends. If the line does not go to the edge of your boxed map area, you label it right along the line. Something like that. But since it reaches the edge of the map, I can label it at either end. Now the next one I'm going to need is a 35. So I look around on the upside of my 30 line. I know which is, in this case, it's to the upper right, because on the other side is the 27, so that's the downhill side. So the uphill side of this, I look and I see a 43, a 52, and a 50, and so I know basically everything except that 30 way up at the top is above this 30 line. So I can do a 35, kind of follow the same profile, because there's no data points to tell me otherwise. I'm not going to change the trend that I'm showing unless data tells me to change it. Now I look for a 40. Well, I have a 40 up here and a 50, and a 43. So I'm going to kind of follow this curvature trend and say, okay, I'm going to bring the 40 line down like this and kind of follow the trend and curve it like that. And so there's a 30, so I know I need to be below that. So I'm going to go like there. And that's my 40. It's labeled. It went through the 40 point because the 40 is the same elevation as the line. If it was a 41 or a 39, it will be near it but not through the data point. I'll still label it on the edges just for redundancy and clarity. But now I have this 40 line, and downhill of it I have a 30. So I know I need a 35 that goes between them. And then I can draw a 30 that goes through the 30 data point. Now I look, my next one going uphill is a 45. 45 is greater than the 43, so I know it's going to be past it somewhere here. It's less than the 50, so below it. Greater than the 42, so above it. And lower than this. So I'm kind of putting dashed lines to help, not necessary, but sometimes very useful when you have a bunch of data. And bring that around, and that's my 45. Now I have a 50, so I know it's going to go through that. I have a 52, so I know it's going to go under the 52, through the 50, under the 59, and everything else is higher. So I can bring this around. And that's my 50. Can do a 55, still below the 59. So I'll kind of go like that. Above the 52, above the 50. But now I notice, oh, the 61 is way over here, and I'm edging pretty close to the 50. So maybe I want to move it a little more over this way. And maybe this one more up here. That's a judgment call. I could leave it close down here because maybe this part is steep and this part is a shallow grade. It's a judgment call. I don't have anything absolute, but I just have to think about what hills look like that I know of, because clearly this is a type of hill. I can tell that by now. And so then I decide to use that point. And I go like that, and that's a 55. And then I can do my 60, close to the 61, below the 67, above that, 59. And a 65, because I do have a 67 here. Now, the way I'm going to do it is kind of an offset hill. So that this one's my 60 and my 65. And now I'm done. Now I can check, did I do everything correctly? At any given line, is everything on one side lower and on the other side higher? So I can pick and say, okay, let's look at the 30 line here. On one side is a 27, and on the other side is everything higher. The only thing is that 30, but I can see, you know, off the map, the 30 lines could connect, everything's fine. Now if I come over and say I check the 50 line, on this side I have a 47 and a 27, and I have the proper number of lines between it. I have a 50 and a 45 leading to the 43, to the 40, 35 and 30. I'm not missing anything. If, for example, I had not drawn this line here, so I didn't have a 35, I had the 30 and then the 40, all of the lines that are there are correct. However, I'm not following my 5-meter interval. I'm going straight from a 40 to a 30. There must be something 35 meters high in between. You can't have a gap in space. There is some point on the hill in between that's 35 meters high. so we need the 35-meter line. So anytime, this is a problem sometimes that I'll see on maps is, I'll have the line near the higher point and a line near the lower point and no lines in between. In this case it was just one, the 35-meter line. Sometimes there could be 4 or 5 lines missing. If this was a 93 and this was a 27, I would need a lot of elevation lines in between to keep that 5-meter interval. So that's a freehand method. Now I need to pause it so I can erase. Oh, doesn't look like it's pausing. So I'll just erase. Next we want to do the interpolation method. And we'll see that generally the interpolation method is going to come out substantially different than the freehand method, and everybody's freehand method will come out different from each other. Occasionally somebody will get something very close to the interpolation method on their freehand. About once every 2 years, 1 out of 40 students will happen to get really close. Occasionally a couple students have maps similar to each other on the freehand, but generally speaking they come out quite unique because it's an artistic endeavor. They can all be following the rules and still all look different. That's kind of the problem with a freehand method, and one reason why interpolation methods were developed. Outside of actual radar or LiDAR to get true topography, an interpolation method is going to be a far more accurate method than just doing the freehand. So we're going to stick with a 5-meter interval, but we're going to start by creating triangles connecting all of the points. So we'll connect the data points like this. We want to try to create as many triangles as we can. So like going like this creates a triangle, but we can increase the number by connecting right there. Basically anything in line with it, another point, is going to get a triangle. In this case we could, this one is offset just enough, we can create that triangle. In this case it's a little too squished down, but possibly we could do that. If you're using a ruler, which you should be using on your paper, it's a lot easier to do, like this 27 to that 40. I think that's too, the 50 is too much in line. I wouldn't worry about it. In this case, it's probably worth having that 27 to 52 line. Definitely over here. On your map for your actual lab, there on one or two of the edges, you'll have a long, thin triangle kind of like this. But the key thing is to make sure that, especially on the inside, you're connecting them all nicely. You're not leaving something like that. You need that connection. Now, once you have that triangle network, which is what this interpolation method is named for, you're going to go through and you measure the length between the different ones, and you figure out where, how many inches or centimeters or millimeters each meter is worth. So like from 61 to 67 is a difference of 6 meters, and I'm not using a ruler. Let me find a ruler real quick. Here we go. Okay, so throw down my ruler. 10 centimeters for 6 meters. So just under, about, off the top of my head, like 1.8 or 1.6, 1.6 centimeters per meter. So that's going to give me a 60. That's 1.6 over, so there's my 60. It's going to give me a 65. That's 8 centimeters over. So there's my 65. And I'm going to come over here and I'll do it for this long one. From 30 to 67. That's a difference of 37 meters. And 27 centimeters. So each meter is a little less than a centimeter, approximately 0.9. Again, I'm doing this division off the top of my head. You can use a calculator and be more precise. But if I'm going from 30 all the way up to 67, I'm going to need the 35, 40, 45, 50, 55, 60, 65. All of those marked along this line. And so at 0.9 centimeters each, the 35 will be right here. So every 4.5 centimeters is another one. So that's 35, 40, 45, 50, 55. I guess I divided wrong in my head. 0.8 is probably going to work better. So 4, 8, 12, 35, 40, 45, 50, 55, 60. So even 0.8 was a little bit overestimating it, but it gives you the idea. If you divide correctly, throw it in a calculator, then measure it out, you'll have all of these points along the way. From the 52 to the 67, I'm not actually going to throw down the ruler and calculate all of these on the recording here, but supposing they were like right there. Oops, no. No. See, I should throw down the ruler. Just trying to do it off the top of my head is not working very well. 5. And you go through and you fill in on every single line. It takes a little bit of time. I just don't want to have you sit here through me doing all of these lines. But the main thing is that, so here's my... Once you do this, each of these marks you have down is like a new data point. It's not technically a measurement. It is an estimate. But it's a calculated estimate instead of just an imagination estimate. And so now you can use them. And you can say, okay, I have a 65, a 65, and a 65. I'm going to connect my 65s like that. I have a 60, a 60, oops, I missed a 65. I cross this line between the 67 and the 65. That's wrong. I caught my error. Now I bring it out here, and that changes the shape of that peak of that hill. Now this line is correct. It does not cross anything in the wrong place, and it doesn't skip any of the 65s. Now I can do the 60, the 60, the 60, and then follow the trend, come around. I know that if I continued outward, I'd have a 55. I'd have a 55. Between the 50 and the 59 is a 55. There is no 55 between 59 and 61. So nothing along this line, except there is a 60 between 59 and 61, which means I need to adjust my 60 line, because now it doesn't connect. So I'll bring it around, and I can just kind of touch like that. It's not going to go on the other side anywhere, but now I've corrected my 60 line. So you can see why you want to do this in pencil. I've already erased and corrected my 65 line and erased and corrected my 60 line. Between the 61 and 52, yes, there's a 55. Between 61 and 43, yes, there's a 55. And look at this, between 61 and 50 is a 60 and a 55. 43 to 61, yep, there's a 60. If I had all the numbers in place already, I wouldn't have had so much erasing probably. 52 to 61, yes, there's a 60. So my 60 line is still wrong. I'm crossing and leaving out stuff. So I can come around here, go like this, and now I have a quandary. I have a 61, and between the 61 and the... And now this is where the recording cut off. We can see the correction to the 60 meter line here, because this data point was 61 meters. When I put a 60 meter mark on this triangulation line, that was an error. Between a 61 and a 67, there is no 60. Going from 61 to 67, we do pass through the 65, so that's correct. The 60 was incorrect. It has now been erased, and we can see the correct marks for 60 following the mouse pointer around. And so the 60 makes a complete circuit and is a proper 60 meter interval contour line, or a 60 meter elevation contour line. And outside of that, we see the completed 55 meter elevation contour line. So the part that was cut off in the recording was just explaining about the error here and doing the correction.